just to reiterate, no lab Thursday, no class Friday. I will be gone with the STEM club to Lincoln, so you have the weekend off. I'm going to put a picture of myself up. No, I'm not, apparently. I thought I could make this thing smaller. Apparently I can't. That's just too big. Let's see, let's do it this way. That's better. Okay, that's a nice small picture. Get that out of the way here. All right, so I did see some people sent some messages to me. I haven't had a chance to answer them yet this morning, but I will do that as soon as I'm available, probably. But let's reschedule some things here. Let's, first of all, we'll open up 15 till the end of today because some questions are in homework 15 that people have. So today is, what is today? The 23rd, right? And then homework 16 we'll make due Wednesday, 25. So that if you have any questions on it, you can get help. And then 16 we'll make due, let's see, 23rd, probably next Monday, which is the 30th. So that you can ask questions if you have any there. So we're going to try to get 2 chapters done this week. Try to get one done today and one done Wednesday. We'll see if we actually accomplish that. We'll move pretty quickly, but like I said, it's not really that hard to understand this stuff. And then that's 15, no, that's 16 and 17. 18 now needs to go to probably, let's see, how many do we have left here? 18, 19, 20, the last one. 2, 3, 4. So if we put 18 on maybe the 2nd and 19 on the 3rd, 4th rather, and 20 on the 7th. Is that finals week?
Yeah, that next week. It's finals week.
Oh, that's not gonna work. So we got to do this. We got to do better. Okay, so 23rd, 25th, and 30th. What is the day? Is the 30th? It's a Monday. The 30th, 2nd, 4th is not going to work. 30th. Let's see, where are we? Here we go. 30th, 2nd. We're going to have to do one probably on a Thursday, both of those weeks.
We only have this week and next week.
Yep. So let's do 30th, the 2nd. We'll come in and meet on a Thursday instead of doing a lab. We'll finish up chapter there, and then we'll do the 4th here, and then this one we'll make due like that next week on the 7th. Even though it's finals week, we won't meet. We'll just give you the weekend to finish it up. But we will do that. We'll finish that one on Friday. But these ones are not hard. I can guarantee you it's mostly just looking things up. So, what's that? Yeah, there's lots of questions, but they're just multiple choice. I mean, you can literally just search for the answer and find it and be done. So it's not that big a deal. So we will do that. And if we have to just like drop off a couple of the last homework assignments, we'll just cut them off if we have to at the end. We won't worry about them. So let's see what we can do today, see how fast we can get through some stuff today with chapters, did we say 16? Let's see if we can get through chapter 16 today and do what we can do here. We'll move very quickly, so if there's something that you want to talk about, tell me. But today is about the solar system. We're going to go through the planets. We're going to talk about planet classifications, their orbits. We're going to talk about Earth a little bit, some of the things that we use on the in the planet sciences. But we're just going to just hit the. In fact, we could probably. I think I have a video we could watch if we had time. I don't know if we have time. What time is it? So we have 40 minutes ish, 39 minutes. Let me check to see what we have for a video. I have one saved here, I think. We could probably just watch a video that covers all these things and not have to worry about me falling behind because I get sidetracked. There's some, good night, what's going on with YouTube? There's some really good videos about the solar system. Physics. Biggest thing in the universe, Earth story, down there's core, inside the Milky Way, full documentary. That's probably too big for us. Too long for us. Journey to the edge of the universe. Solar system. Let's look for something. 20 minutes. That's 48 minutes. The solar system song. There's some really funny songs out there. Crash course, our solar system. Don't want the birth of the solar system. Well, let's try one out. I hate to do this without previewing the movie just to make sure that we don't waste our time, but let's try it out anyway. I'm willing to take a little risk here.
That's good.
Go-getters, get two with Dunkin' Go-Tos.
Oh, that is good.
2 sandwiches for $2, $3, or $5. America runs.
I
on
wouldn't
Dunkin'.
recommend it. They're really greasy. Try it once.
4.6 billion years ago, our sun started to form about 2/3 of the way out on one of the spiral arms of the Milky Way. Our sun is a third-generation star, starting from gaseous clouds and dense nebulae containing many heavy elements. It condensed under the inexorable pressure of gravity until it was hot and dense enough to experience nuclear fusion at its core. As stars go, our sun is an average yellow star. But it is so massive that it contains 99.8% of all the mass in the solar system. Its radiant energy supports almost all life on Earth, and it drives Earth's climate and weather. It is almost 900,000 miles in diameter. It has a core temperature of about 15 million degrees, and its surface temperature of about 6,000 degrees. The sun will be fairly stable over the next 5 billion years, at which time it will enter its red giant phase. It will expand enormously so that its outer layers will reach the current orbit of Earth, giving it a diameter of almost 200 million miles. After that, it will live a few billion more years as a white dwarf.
Mercury is the smallest planet in our solar system. It is only about 3,000 miles in diameter and has a surface that is pockmarked with craters like our own moon. It is the innermost planet and has an elliptical orbit that takes it within 28 million miles of the Sun at its closest approach, and out to 43 million miles at its most distant. It takes Mercury 88 days to orbit the Sun.
And figure this out, sports fans. Although it rotates once every 59 days, the day on Mercury is 176 Earth days long. Oh, it doesn't really have a tail. We added the one in the video to make it easier to see and to show its orbit. And although the scale is correct for the size of the Sun relative to Mercury's orbit, we are showing the planet 100 times larger than it would be if it were to scale as well. Except for the Sun and the Moon, Venus is the brightest object in the sky. And since it is closer to the Sun than we are, it shows phases like the Moon. Shrouded in permanent clouds, Venus rotates on its axis every 243 days, and it rotates backwards from the other planets. It is only slightly smaller than the Earth, and it orbits the Sun every 225 days, at a mean distance of 67 million miles. But its surface is terribly inhospitable. The atmospheric pressure at the surface is 92 times that of the Earth,
We would
similar
just
to the
be
pressure at
crushed.
half a mile down
If we
underwater.
tried to go stand on Venus, we would be crushed.
Its
by the
temperature is a
pressure.
balmy 900 degrees Fahrenheit. All in all, not a good vacation spot.
We would crush it and be burned to death.
Our Earth is 8,000 miles in diameter and rotates on its axis, causing sunrise every day.
Almost the same size as Venus. They're almost exactly the same size.
It is the largest of all the planets that have a solid surface, and it possesses an unusually large moon or planet of its size. Since the moon circles the Earth, we think of the moon's motion as circular. But since the Earth-Moon system revolves around the Sun at about 65,000 miles per hour, the moon's motion in the solar system isn't much different from our own. At 93 million miles from the Sun, the Earth is the third innermost planet, and is the only place in the solar system that we know of that has liquid water. Mars is the planet most similar to Earth in terms of habitat. Although smaller than Earth and Venus, it has a thin atmosphere and probably had liquid water on its surface in the past. This attracts our interest and has prompted us to send a plethora of probes. It has two orbiting irregular-shaped rocks, graciously called moons.
Only 1/3
Which
of
are
the probes
probably
we sent to
captured
Mars have
asteroids.
actually made it successfully.
A day
We
on
have about a
Mars
30%
lasts about
success
24
rate
hours,
sending things to Mars.
very comparable
In
to
case
our
you're
own.
wondering.
The volcano called Olympus Mons, or Mount Olympus, is the highest known mountain in the solar system.
3 times higher than
It is an extinct
Everest.
volcano and is over 3 times the height of Mount Everest. Mars is the fourth planet from the Sun and completes its orbit every 2 Earth years.
the gravity on Mars is about 1/3 that of Earth.
Jupiter is huge. If it had only been a little larger, it could have become a brown dwarf star circling our Sun. It is a gas giant and has no solid surface. Its atmosphere forms bands of poisonous clouds that circle the planet in opposite direction.
This is actual imagery.
The
of-
giant red spot is a huge storm that has been raging for hundreds of years. 4 of its many moons are so large that Galileo spotted them with his primitive telescope in 1610.
You can see those
In
4
addition to
moons
moons,
with a pair of binoculars
all of the gas giants have rings,
on a good night.
but Jupiter's rings are so faint they are not visible.
They show up as little dots in front of Jupiter, usually.
The fifth planet out, Jupiter orbits the Sun at a distance of 480 million miles and takes almost 12 years for one complete circuit. Notice the large separation between the orbits of Jupiter and Mars. This is the realm of the asteroid belt. It is the debris of a planet that failed to form because of Jupiter's gravitational influence.
In other words, a planet tried to form in between here, but Jupiter's gravity kept breaking it apart every time it came around.
Saturn is the second largest of the planets. Only
My
Jupiter
favorite.
is larger. Like all the gas giants, it has a system of rings. And the rings of Saturn are glorious. Like Jupiter, Saturn also has dozens of moons, and one of them is particularly notable. Titan is the second largest moon in the solar system, and it possesses an atmosphere remarkably like Earth's. It is primarily composed of water, ice, and rocky material. It is even possible that under the clouds and surface ice, Titan has liquid water, and maybe even microbial life. It is 50% larger in diameter than our own moon, and 80% more massive. Saturn takes 29 years to orbit the Sun, and does so at a distance of 890 million miles.
Saturn is almost 10 times as far away from the Sun as we are.
Uranus rolls on its side. It is an icy giant of a planet, the third largest in the system. Like the other giants, Uranus has a ring system and numerous moons. It is the seventh planet out, and it orbits the Sun at a distance of 1.9 billion miles. A year on Uranus lasts 84 Earth years. Because of its extreme axial tilt, seasons on Uranus are worth a look.
So instead of
At
just
the
being
time near the
twice as far
solstice,
out,
one pole
Uranus is
continually faces the Sun, while the other faces
220 or
away.
200 times further out.
Only a narrow strip near the equator
Uranus is really far out.
experiences Uranus' 17-hour day. At the other side of Uranus' orbit, the orientation of the poles is reversed, so each pole gets 42 years of continuous day, followed by a 42-year night. Okay, let's head to a point high over the ecliptic, so we can see the relative sizes of the orbits of the sunward planets.
What's that?
The smallest planet.
I've been asleep for 42 years.
Yeah. So Uranus,
Happy birthday. Oh, thank you. I'm dying next year.
let's see. So Uranus does have that strange thing going on, and it's way far out beyond Saturn. We built a solar system to scale here in town last summer. The sun was over here at this elementary school. What's it called? Osgood. We put the sun there, and it was 6 feet in diameter. And all of the inner planets, all the way up to Mars, were between Osgood and the driveway over here to the college on Willow. And then Jupiter was at the end of Willow, down by whatever road that is, Walker. Yeah, Jupiter was on the corner of Willow and Walker. Saturn was down at the park by the freeway there, that memorial park there, and Uranus was at Nebraska Land Bank. That's how much further Uranus is. And then Neptune was at the Children's Museum all the way across the other side of downtown. And then Pluto, can you guess where Pluto was?
River.
It was at the river. It was at Cody Park. So it's to scale, and our sun was 6 feet in diameter. The Earth was the size of your pinky. And Pluto was the size of the head of a pencil. You know, the biggest planet that we had, which was about the size of a volleyball, was Jupiter, of course, and that's the biggest planet we had. with the Earth being 6 feet in diameter. So it gives you an idea of the scale. Solar system is a humongous place. So, oh, and in our solar system that was set up like that, the speed of light was about like a very slow walk. So if you walk heel to toe very slowly through our solar system, that's how fast light travels from the sun outward to the outer planets. And getting all the way out to Pluto takes hours doing that. Getting to Earth takes several minutes. I think it's 6 minutes for light to travel from the sun to the Earth or something like that.
Experiences
Sorry, what? Is it 8 minutes?
Uranus' 17-hour day. At the other side of Uranus' orbit, the orientation of the poles is reversed. So each pole gets 42 years of continuous day, followed by a 42-year night. Okay, let's head to a point high over the ecliptic.
Oh, this is what I was going to say, is the ecliptic is the plane where all the planets rotate. All the planets in the solar system rotate within this one plane except for 2 of them, and we're about to learn about these 2.
So we can see the relative sizes of the orbits of the sunward planets.
Actually, I think only one goes outside the ecliptic, but anyway. See how much further out Uranus is than Saturn?
Neptune is a blue world. It is the smallest of the giant planets in our system, but still 30,000 miles in diameter.
It's about 4 times bigger than Earth. Well, 4 times
Since
bigger
the
than
demotion of Pluto, it is the furthest planet from the Sun. Neptune's rings are very faint, and of its 13 moons, only Triton is massive enough to be round. It rotates every 16 hours and orbits the Sun every 165 years at a distance of 2.8 billion miles.
So Uranus and Neptune are actually fairly close to each other, and that's actually how Neptune was discovered. Neptune, they didn't know it was out there for the longest time, but they did notice that Uranus, every once in a while, its orbit changed a little bit. It wobbled a little bit in its orbit every once in a while. And that was because Uranus and Neptune are so close to each other that when they are on the same side of the sun, they actually attract each other and pull each other out of their orbits. And so that was noticed by people studying Uranus, and they said the only reason that could be doing is that there must be some planet out there. And they knew where it should be, and so they looked really for a good long time, really hard, did some really good some research there, and they were able to detect Neptune. It's very difficult to detect the light shining off of these planets because they're so far out, very little sunlight shines off of them.
Pluto is now deemed a dwarf planet and a member of the Kuiper Belt. The Kuiper Belt is a region of the solar system that extends just beyond the orbit of Neptune, at about 2.8 billion miles out to about 5 billion miles. Like the asteroid belt, it is crammed with many small bodies orbiting the Sun, most of which are frozen methane, ammonia, and water. Here's a size comparison. Earth, Ganymede, Titan,
These are all moons,
our moon, and several bodies from the Kuiper Belt. Currently, the largest known Kuiper Belt bodies are Eris, Pluto, Sedna, and many more without formal names like FY9 and EL61. A day on Earth is a deceivingly simple concept. Today we'll examine that day on Earth in detail, perhaps uncovering a few surprises. A day is the length of time it takes the Earth to spin 360 degrees on its axis. Or is it 361? Here's a simple model showing the Earth, the Sun, and some background stars. The Earth travels around the Sun in an ellipse, with the Sun at one focus. The model, of course, is not to scale,
Let's begin our examination at noon one day. The sun is directly above the red line. That will be our reference point. Watching from a high vantage point, we see the Earth complete 360 degrees of rotation. But during that time, the Earth has also moved a bit in its orbit. So even after a 360-degree turn, the sun is not directly above the same point on Earth that it was at the beginning of the spin. It is not noon of the next day. The red reference line needs to spin a little more than 360 degrees to get us to noon. The 360-degree rotation is called a sidereal day, while the noon to noon rotation is called a solar day. Earth orbits the sun once for about every 366.26 sidereal days, and once for every 365.26 solar days. Not only that, the length of a solar day varies throughout the year, and for two different reasons. First, because of its orbit is an ellipse and not a circle, the Earth moves faster when it is near the sun and slower when it is further from the sun. So the little extra amount of rotation that the Earth needs to do to get from noon to noon changes throughout the year. Second, because the Earth is tilted on its axis, the little extra rotation to get from noon to noon is largest at the solstices and smallest at the equinoxes. So solar days grow progressively longer as we move from equinox, March and September, to solstice, June and December. And did we mention the Earth's spin is slowing down? And the length of the solar day is increasing due to gravitational tides between the Earth and the Moon? The length of the mean solar day is increasing at a rate of approximately 1.4 milliseconds every century. 2 billion years ago, there were about 750 days in a year. Now let's talk about daytime. That period out of 24 hours when it is light outside. Day versus night. Due to refraction and scattering of light by the atmosphere, there can be daylight even when the sun is slightly below the horizon. But day length is usually about the sun's disk being on or above the horizon. So the day begins the moment the sun's disk appears during sunrise, and ends the moment the sun's disk disappears during sunset. At the equator, daytime and nighttime are equal to within a few minutes. But at distances north and south of the equator, the length of the day varies with the season, with the longest and shortest days being on the solstices. At the poles, once the sun has risen, it stays up for 6 months before it sets again. And during the course of each day, it travels in a complete circle around the edge of the sky. Because the Earth travels at different speeds in its orbit, the sun is north of the equator for almost 4 days more than half the year, and the length of the average day in the northern hemisphere exceeds the length of the average day in the southern hemisphere by a few minutes. In the northern hemisphere, the Arctic Circle is the southernmost latitude where 24-hour daylight can occur at least 1 day in a year. In the southern hemisphere, the Antarctic Circle is the northernmost latitude where 24-hour daylight can occur at least 1 day in a year. And daylight savings time is like the old man who cut off one end of the blanket and sewed it on the other end to make it longer.
What's that? One
A
more time.
blanket is an Indian proverb.
Oh,
A year on Earth is measured by one complete trip around the sun. Seems simple enough, but there is a problem. The Earth doesn't travel in a path around the sun that returns to its starting point. So how do we know when a year starts or ends? Well, one way, called a sidereal year, measures our orbit against the distant stars. As viewed from the Earth, our orbit causes the sun to appear to move through the constellations of the zodiac on a path called the ecliptic.
which of course is
And
why
when
the
the sun
zodiac was
returns to its
created.
starting point, a sidereal year has passed. This motion is difficult to observe directly because the stars cannot be seen when the sun is in the sky. However, if you look at the sky before each dawn, the annual motion is very noticeable. The last stars seen to rise are not always the same, and within a week or two, an upward shift can be noted. As an example, in July in the northern hemisphere, Orion cannot be seen in the dawn sky, but in August it becomes easily visible. Measuring a year this way gives a period that is 365 days, 6 hours, 9 minutes, and 10 seconds long. Another possibility is to measure the year against the passing of the seasons. Because of the tilt of the Earth on its axis, the position of the sun in the sky changes from day to day throughout the year. If we were to take a picture of the sun at noon regularly throughout the year, we
That's
would
what
see
counts for
the
your
sun
sun
moving
angle.
on this path called an analemma. On the days in its orbit when the Earth is at a maximum tilt towards or away from the sun, the length of the daylight is at a maximum or a minimum. These days are called solstices, and the sun will be at the top left or bottom right of the analemma. On the days when the Earth's tilt is perfectly sideways to the sun, the day and night are equal in length. These are the equinoxes, and the sun will be at a latitude-dependent position in the analemma. When the sun goes from one vernal equinox to the next, a tropical year has passed. Measuring this way gives a year that is 365 days, 5 hours, 48 minutes, and 46 seconds long. The length of a year on Earth is affected by several gradual and cyclical changes in its orbit and its tilt. First, there is the precession of the Earth's axis. Over a period of about 26,000 years, the Earth's axis traces out a circle in the sky. One result of this is that the North Star changes over time. Right now, the Earth's axis points towards Polaris. 5,000 years ago, the axis pointed to a star in the constellation Draco. And 12,000 years ago, the brilliant star Vega was the pole star. And because of the 26,000 year cycle, Vega will be the pole star again in 14,000 years. The precession of the equinoxes is caused primarily by gravitational forces of the sun and the moon acting on the Earth. While the axial tilt is the primary cause of seasons on the Earth, the distance from the sun, which changes throughout the year because of the elliptical shape of the Earth's orbit, contributes a small bit of temperature variations throughout the year as well. When the axis is aligned so it points towards the sun during perihelion, one hemisphere will have a greater difference between the seasons, while the other hemisphere will have milder seasons. The hemisphere, which is in summer at perihelion, will receive much of the corresponding increase in solar radiation.
I think I'm going to stop it there. And we're going to go back to our book. because that covered a lot of stuff that is good for us, but I want to talk specifically about, let's see, let's go through and make sure that, I want to make sure that we have all the stuff that we need to make calculations. So they talk about some of the different scientists, Copernicus and Kepler, Tycho Brahe, who did all these studies of the planets going around. And this is one thing that we want to talk about, which is Kepler's laws. In Kepler is, he was an astronomer and a physicist who figured out some of the motions of the planets, in particular that the planets have a motion of an ellipse. Instead of circular orbits, they're actually kind of these ovally orbits with these two things called focuses, where the sun is at one focus and the planet follows on this path around here, which is determined by the distance between an equal distance between the two focuses. So if you take a piece of string at a particular length and tie it between these two pins and then stretch it out and then draw a circle so that that string is always stretched out, or draw a shape so that string is always stretched out, you will get a distance to this path that is always the same distance if you add up the distances from that path to this focus and that path point to this focus. Now, understanding that is not really the important thing. The other important thing is that you get this kind of elongated ovally shape, and this right here is important. One of Kepler's laws says that during a particular amount of time in the orbit of any planet, for example, if you do 5 days. So if you go 5 days from January 4th and the planet moves this far on its orbit, this little wedge that's mapped out in its path would be the same area as this wedge over here if you went 5 days on July 5th when the planet is further away from the sun. It sweeps out a smaller angle here and a skinnier wedge, but the areas end up being the same. And the result of that, the reason for that is because the planets are moving faster when they're close to the sun and slower further away from the sun. So that's one of Kepler's law, the law of equal areas. The other one is this one right here, which is the law of called the harmonic law, or the law of periods, which means when you want to know how long it takes a planet to go around the sun, you can actually calculate it using this law, where you use the semi-major axis. Now, what's the semi-major axis? When you have an ellipse like this, you have a long direction, the long direction of the ellipse, and then you have the short direction. The semi-major ellipse is from the center of the ellipse out to one side, and that's the semi-major radius of, and this is the semi-major axis. So this is the axis, actually, the major axis, and half of it is the semi-major axis. So that's the r, or the radius of the major axis in this equation. So if you want to calculate how long it takes a planet to go around, all you need to know is the semi-major radius, or the semi-major axis of its orbit. And so if they tell you that, you cube that number, and then you multiply it by this k, which is a constant that they give us right here. It's equal to 1 year over what we call the astronomical unit, which is the distance to the Earth cubed. And so if you're using this one, it's a little bit confusing, but it's not really difficult. So in this particular case, we want to calculate the period of a planet's orbit whose semi-major axis is 1.52 AUs. That means 1.52 times the radius of the Earth. You just leave it in these units, 1.5 AUs, the distance from the Earth to the sun. And so if we had a planet that was 1.5 times the distance from the sun, we plug that number into this equation for the AUs down here, we get, for the R here, R cubed. So we get 1.5 AUs, and then we plug in for K, 1 year squared over AU cubed. And so that's a very simple number. It's just 1 where the units cancel out here in the end. And then we have to take the square root to find the period. So if you take the square root of that period, square root of this number, 1.52, is going to give you the answer 1.87. And so you'll end up with 1.87 years, Earth years, for that particular period of that planet. So if a planet was 1.5 times as far, or 1.52 as far away from the sun as the Earth is, then it would take 1.87 years for it to go around the sun. It has nothing to do with the mass of the planet. It has everything to do just where it is in the solar system. So that's a very interesting thing that came out of Kepler's laws. And here are some of the information about the planets in our solar system. Distance from the sun, the orbital period, the number of years it takes for it to go around once. This is the relative mass of these planets relative to the Earth. So the sun is 333,000 times the mass of the Earth, whereas Mars is 0.1 times the mass of the Earth. And Mars is almost about 1/10 the mass of the Earth. And of course, Earth is 1. So this is relative mass of Earth to, or of planets and sun to the Earth. And this is the relative diameter of these planets to the Earth. So of course the Earth is relative to itself, so it's just 1. But Mercury is about 1/3, it's about 0.38, the diameter of the Earth. And Venus is 0.95. It's almost the same exact size of the Earth, whereas Mars is about half the size of the Earth as far as diameter. And you go out here to Jupiter. Jupiter is more than 10 times the diameter of the Earth. So those are some of the things that they maybe didn't point out especially, and certainly Kepler's laws, they didn't really explain in great detail on how to use them. Here we have this idea of prograde motion and retrograde motion, where this is the revolution around the sun. Almost all the planets go around the sun in a particular direction. So if we're looking down at the north pole of the Earth and the north pole of the sun, they go around counterclockwise, the planets go, except for Venus and Uranus. They go in retrograde motion. They go the other way around, clockwise around, if you look down, away from, or down from the North Pole. Here's some more things here. So conjunction. So conjunctions are when two planets are on the same side of the sun and they line up between the Earth and the sun, so that they block out the sun, or the sun is blocked out on one of those planets. And there was actually a major conjunction just last year where all of the planets in the solar system were all on the same side of the sun, which was really cool, because when all the planets are on the same side of the sun, that means you can see them better because they're all much closer to us and they're all lit up better for us. When they're on the opposite side, they're much, much further away, especially those outer planets. So last year was a great year for seeing them. Of course, many of them are still kind of on the same side because they don't go around the sun as fast as we do. But we go around the sun much faster, so hopefully we will be able to come around and catch up with some of those outer planets again. But the inner planets are going around faster. So we've got a good time. It's a good time right now, really, for these next couple of years to observe the planets, these next few years, actually, a couple of decades maybe, to observe the planets while these outer planets are all kind of on the same side of the sun, and the inner planets are kind of coming around to the same side of the sun again. Last year we got out the telescope several times to see Saturn, because we were on the same side of the sun as it was, and we will be again towards the end of, I think we are now actually towards right now, pretty close to Saturn. So we might have a chance to get it out and get the telescopes out and look at Saturn. Saturn is my favorite thing to look at, of course, in the solar system, just because it's so cool with its rings. But anyway, lots of things to talk about. Why do we know that the Earth? Why did we learn that the Earth is round and that it's going around the sun? Well, one of the things is pendulums. You can set up a pendulum. If you set up a very long pendulum with a nice heavy weight on it and let it and kind of keep it going for several days, you'll notice a pattern that the pendulum has this precession, that it doesn't just swing back and forth in the same direction on the Earth. It actually rotates around, and in many museums and things, they have these focal pendulums knocking over little things on the floor or whatever, showing that they move around and around once every 24 hours, where the Earth is actually rotating underneath the pendulum. So that's a very cool illustration of how they discovered this, that the Earth is going around. Also, the precession of stars in we call it the parallax of stars. As we look at stars that are farther away than nearby stars, we notice that they appear to be moving back and forth in the sky. But the reason for that is because we're actually moving back and forth in our orbit, back and forth like this. So that's kind of, it's another thing that was discovered. That's called parallax of stars. Okay, go ahead. So there's just so many things that are interesting about the solar system, and there's most of this stuff you can just look up, like I mentioned before. We're going to learn more about some of these things in the coming chapters. So if you have any questions about the things that we studied so far, feel free to email me and call me and everything else, or come into my office. Some more parameters of the planets as far as their surface temperatures and days and densities and other things. There's just lots of information that we learn, but not lots of calculation that we do here. Some really cool pictures, of course. Here they talk about gravity assist, where we use the gravity of one planet to slingshot us off to another planet. Just so many very cool things that have been discovered recently, particularly if you go further out into the solar system. We've discovered more planets out in the Kuiper Belt. We've possibly got a really, really big protoplanet out in the Kuiper Belt, like a planet maybe bigger than Earth out there. They're trying to find. They've detected the possibility of a planet out there that could be maybe even 10 times as big as Earth, kind of like as big as like Jupiter maybe. But they didn't see it, they just detected its gravitational pulling on other things, so they're still kind of looking for it. There's just so many cool things going on as we look further and further out into our solar system. And so that's where we're going to kind of leave it at this point. And we're going to talk more about beyond our solar system next time. So we'll see you guys on Wednesday, and go ahead and get started on the homework, and have a good day.